Hello students, welcome to the class once again. And I know you must be excited to learn more in this chapter. We have already completed the concept of work energy theorem. I told you about the last class. I told you about law of conservation of mechanical energy. I told you the sum of potential energy and kinetic energy is equal to total mechanical energy. Today we will be learning about power. And before starting the chapter, I know you are all very young. You go to the market and you see so many vehicles like super bikes, cars, and whenever you go to a showroom to buy all these vehicles, the showroom owner specifies you, it gives the characteristics of the engine, and it says that the specification of engine, it says the power of engine is this much horsepower. Actually, what can you derive from that value? And we all have the idea, if you go to a vehicle, it says that its power is 220 cc, its power is 550 cc, its power is 700 cc. We get an idea about how easy it would be and how fast it would be to accelerate the vehicle. So power is nothing, it's actually rate of doing work. So let's start this chapter understanding the concept of power in this class. Let me tell you this very simple, easy and interesting. Power, it is the rate of doing work. The rate at which a body will do work or an engine will do work, that is the power of the body or the engine. It is the rate of doing work. It is defined as rate of doing work by an engine or any object. Now if I say rate of doing work, that means the total work done by the time taken to do the work, that will be power. So power in simple equation, we can say power P is equal to total work done divided by total time taken. Now what is total work done? We all know that if you apply a force, the work done by that force is given as F dot delta x, that is equal to work done. So if I write power is equal to work done divided by time, and we know that if a force acts on an object, that means the work done by the force will be given as F dot delta x, and let's say time taken is delta t. What is this delta x by delta t? That is actually, I know that you're thinking about the speed. Yes, it is speed and it is the average speed if it is v. So we can write power is equal to fv. So we get this one thing, power equals to fv, where v is the average speed. Now from this equation, we actually get the average power delivered by the object or delivered by the engine which is actually doing the work. Okay, so we can say the average power is equal to force into average speed. So if we need to understand the concept of average power, it is simply power average is equal to product of force and speed, where if I write about speed is actually the average speed during the entire interval of its journey. Now force has to remain constant for this entire, because we have used F dot delta x. This is the constant force that has to be acting to find this average power. Now this is not the case which is possible in all the cases. Force can vary, and depending on the application of force, what magnitude force you are applying, the speed, the velocity will also change, and at every instant we will be having a different speed or different velocity. So that will give us, if we take the product of force and velocity, so that will give us instantaneous power. So if at any instant we have the force applied on an object is F and its speed is V, so power delivered at that instant will be equal to dot product of force with velocity. So just simply you take dot product of force and velocity, you'll be obtaining the power delivered at that instant of time. So instantaneous power delivered at that particular moment of time will be dot product of force and velocity. This is how we are going to evaluate power. Now one thing we need to remember, the basic thing, it is actually rate of doing work, that is total work done upon time taken. It's actually W by T. And then we have the average power delivered is FV, we'll get here. And if you want to require, if you need, what is the instantaneous power delivered, that will be given as F dot V. Let's go to a simple question. We'll do very basic questions based upon this concept. Let us say, it says that an engine is actually pulling up or trying to pull up water from a height of, or let's say from a depth of 20 meters. An engine lifts up an engine lifts up water. It's actually motor engine. We have in our home the motor which is actually required to lift the water. So an engine lifts up water at the rate of, let's say, lifts up water at the rate of, let's say, 60 kg per minute, at the rate of 60 kg per minute. If the depth from where the water is raised is given as 20 meter, if depth from where water is raised is 20 meter, from where water is raised is 20 meter, find the power delivered by the engine. Find the power delivered by engine. Find the power delivered by engine. Not to worry about this. If you remember the basic definition of power, power is actually what? It's rate of doing work. So if we evaluate what is the work done, what is the work done we are doing per minute, because we are lifting water 60 kg per minute. If we try to find out what is the work done during that 1 minute, and now if we divide that work done with time of 1 minute, we'll get the power delivered. It's very simple words. If we write solution, first thing, we are lifting 60 kg of water per minute. So work done in 1 minute. Work done in 1 minute. This will be actually nothing but, cause actually what is happening, just see this diagram. Let's say you are lifting water which is present here at the bottom. It's, let's say its depth is 20 meter. This is what has been provided in the question. Now from here the engine is actually lifting water 60 kg per minute and is trying to bring this water here. 60 kg per minute water has been brought here. So work done will be actually, you have to lift this water against the force of gravity. So work done will be mgh. So this will be mgh, so that is 60 kg multiplied by g as 10 multiplied by height as 20. We'll be having this as 6 into 2, 12,000 joules. 12,000 joules. This is the amount of work done while the water was lifted through a height of 20 meter, you can see here. Now this much work is done 1 minute. So power delivered, therefore power delivered will be given as work done divided by time. And we know work is done here 12,000 joule. 12,000 joule divided by time taken, that is actually equal to 1 minute. So we can write it as in SI unit 60 seconds. So we are going to get, we can cancel out this 1 0. We'll be having 6 into 12, 200 joule per second. This is the value of work done or power delivered by the engine. So I have written the units as the unit of work divided by unit of time. So with this question, we can actually sum up to also know the units of power. So let's write down the unit of power used. The units of power used, it's simple. In very simple terms, since it's actually ratio of work done with time, so the first unit that we are going to get, that is actually joule per second. This is one unit. Now this joule per second is known as watt. So this is actually the unit 1 joule per second is known as 1 watt. And this is written as capital W, 1 watt. Now this is actually very small unit, 1 joule per second, that is 1 watt. It's very small unit of power. So we use some larger units. In general, you will see whenever you see the big vehicles, their power is given in horsepower. Now what is that horsepower? 746 watt is equal to 1 horsepower. You must be seeing the ads of big vehicles like truck or tractors. With that ad, it's also given that its horsepower is 3.5 HP, or sometimes it will be given 5 HP. Now that is actually, HP is actually horsepower. this is actually written as 1 HP. So 746 watt is equal to 1 HP. Sometimes in some numericals we use the value of 1 horsepower nearly equal to 750 watt. Sometimes we use this also, sometimes, but the original relation between 1 horsepower and watt is 746 watt is actually equal to 1 horsepower. This was a basic example of power. We can try more examples on this. Now actually let us do one more example related to this only, and we'll just change the variables and change the statement of the question. A company makes an engine. A company makes an engine and specifies its variables. A company makes an engine and it says that this engine can do certain amount of work. A company makes an engine and it says that this engine has a capability of lifting 100 kg load through a height of 50 meter. It says that it has capability to lift 100 kg load through 50 meter in, let's say, in 2 minutes. This is what the specification of the engine has been given. It has the capability to lift 100 kg load through 50 meter in 2 minutes. So what I'm going to do, I'm going to find power of engine. Find power of engine. See, it is so easy to evaluate this one. Let's do the solution of this question. We have, it can lift a mass 100 kg through a height of 50 meter. So it's going to lift it through a height of 50 meter and it will place here. Now, if this engine lifts this block from this position to this position, it has to do some work. Let us try to evaluate what is the amount of work done as it lifts the block. So work done will come out to be mgh, because what amount of work it does, that will be equal to just against the gravitational pull, how much amount of work it will do. Well, it has to apply a force mg in the upward direction and it will pull it through height h. This will be the value of the work done by the engine. So we got the value of m is 100. So this work done will be in joules. So just simply you can see it's 5 and 4 zeros. 5 into 10 to the power joules. This is the value of the work done. Now it takes time 2 minutes. So power delivered by the engine will be equal to work done by time taken. This will be simply 5 into 10 to the power 4 joules divided by 2 minutes, so 2 into 60 seconds. How simply we can evaluate? We can write this as 5 and 4 zeros, 6 into 2, 12. Let's keep it in this way and further we will simplify this. You see here 1 0 1 0 will be cancelled out. We'll be having 2 into 6 12, 5000 divided by 12. See, 12 into 4 48. So we'll be having 4 and then we'll be having again 220 here 400, or let's keep it in this way. Let's simplify. Here we'll be having first 5000 divided by 2 will be 2500 by 6. 2500 by 6, or in very simple words you can simplify, you will be getting 1250 by 3, and simplified further you will be having 3 4s are 12, 3 1s are 3, 220, 3 6 are 18, 220 again, so 416.67 joule per second, or we can write this as 416.67 watt. This will be the power delivered by the engine, and you can check rest of the things. Yeah, it's okay, we have done. This is how we are going to evaluate the power. And sometimes you'll be given that a body moves with a speed, fixed speed, and force is acting on the body, and you have to evaluate the instantaneous power delivered by that force, and that will be coming out to be F dot V. You'll be given with the speed, and in several examples we'll see the concept of when you're going to do dot product of force and speed. Now in this class, let's do some standard good questions which is asked directly in the examination, and in some of the objective question you require to practice such questions. So let's do them. That's required. The first question of the day we have, it's given that a chain of mass m and length L is hanging from a table with 2/3 of its part on the table. It says that a chain of mass m and length L hangs from a table with 2/3 of its part on table, with 2/3 of its length on table. The first statement should be very much clear to you. I know you must be drawing the image in your mind, you must be thinking about the image, how it would look like with 2/3 of its length on table. Find the work done by a man in lifting the chain completely on the table. Find the work done by a man, find the work done by a man in lifting the chain on the table. Now how to evaluate this? How to evaluate this? Its mass is m, its length is L, and he's slowly lifting the chain. He wants to bring up the chain on the table. Let us draw the diagram how the chain will look like. We have this case in this way. This is the table. Okay. Now the chain is hanging with 2/3 of its length on the table and 1/3 of its length hanging in this way. To show it exactly 2/3, we can actually elongate it so that we may have the idea that more part is hanging and a less part is hanging. More part is on the table and less part is hanging. Hope that this is clear to you. This part is hanging. Now if a man is trying to pull this chain and bring it completely on table, this table, forget about the friction force that table will be exerting on the chain. We need not to consider about that. Now this part is hanging. First thing, this part is hanging and we want to lift a load. That means we have to do some work. So how much work is done on this chain? Now see here, this part of chain will be having some mass. Now if I slowly lift this part, that means mass that is hanging, that is decreasing with time. So initially I have to apply more force to actually balance its weight. Finally, as I lift up the chain, I have to apply less force, and when only this much part will be hanging here, we have to apply the minimum value of force. Now how to do such kind of question? What we are going to do, we are going to use the concept of differentiation and integration here. See how to approach with such kind of question. Let us take at a distance x from top a small segment of the chain of length dx. From top for length x, what I'm going to do, I'm going to consider a small segment of the chain whose length is given as dx. Now this part of chain, just you see this part of chain. Suddenly this part of chain will be having some mass. It is very small segment and you are going to lift it, and now let us see what will be the work done to lift only this small segment of chain to bring on the table. Now this work done will be simply the work done against the gravitational pull. It's a small segment. So take a small segment at distance x from top of table